We're going to go through the 7 most important data structures today and explain them as simply as possible. These are extremely important to learn whether it's for coding interviews, computer science class, or building projects. We'll be going through the list from easiest to hardest, so beginners have a better idea of where to begin. We'll go over a simplified explanation for what each data structure is and talk about common uses for that data structure. I'll also be putting the time complexity for common operations on screen, but if you don't know what that is, don't worry. I'm just including it on the screen for people who want to see. Let's not waste any time and get right into it. Arrays. Arrays are ordered collections of data. Typically, the data is all of a similar type, like integers or strings, but some languages also allow for differing data types. An example of a real-life use for an array would be if you had temperatures for the next 5 days and wanted to store them so your program could access them. Arrays are used all the time and for pretty much everything, so they're definitely the most important data structure to learn first. One of the amazing benefits of using an array is that it's very easy to find any element, as each element in an array is assigned a number called an index that you can use to find it. This form of numbering is often called zero-based indexing. Arrays are very good for reading elements but can a bit less efficient when it comes to insertion or deletion. Linked lists. While arrays were fast at reading elements and a bit slower at inserting or deleting, linked lists are a bit slower at reading elements but fast at inserting or deleting. Linked lists are similar to arrays in that they also store ordered lists of data elements. However, a huge difference is in the way they are stored in memory. Each element of a linked list has what we call a pointer, which is basically the address of the next element of the list. As a result, elements in a linked list do not have to be stored beside each other. You can store the next element in any location and the previous element will point to it. The disadvantage of this is that linked lists do not have indexes, as the elements are not stored right beside each other. This means that to find an element, we have to go through the list starting from the beginning. Hashmap. Remember how arrays had values stored, and for each value there was an index that numbered them? Well, hash maps are essentially the same thing, except that you can choose what the index is, which hash maps call a key. The key and its value are commonly known as key-value pairs. Hash maps are fast O of 1 for both inserting and removing elements. Hash maps go by a few different names. They are sometimes called hash tables, or if you know Python, they're called dictionaries. Stacks and queues. The most simple way to describe stacks is to think of a stack of plates or pancakes. The first plate goes on the bottom, the last plate goes the top. Stacks are LIFO structures, which stands for last in, first out, because the last element in is like the last plate that goes on top the stack. When you go to grab a plate, this last plate on top will be the first you take off. Stacks have 3 common operations, which are push, pop, and peek. Pushing is when you add a new element to the top of the stack. Popping is when you remove the topmost element from the stack, and peeking is when you're just taking a look at what the element at the top of the stack is. All of these are very fast, which is why stacks are optimal for certain problems. Queues are the opposites of stacks. The simplest way to think of a queue is like a lineup at a grocery store. The first person in the line will get serviced first, and every additional person who joins the line goes at the end. Queues are FIFO structures, which stands for first in, first out, because the first element in is the first element to come out. Queues have very similar operations to stacks, which are enqueue, dequeue, and front. Enqueue is like push for a stack and is when a new element is added to the back of the queue. Dequeue is like pop for a stack and is when the element on the front of the queue is removed. Front is like peek for a stack and is when you take a look at the frontmost element in the queue. Queues are more frequently used than stacks, especially in real-world programming. Think of YouTube playlists. When you start watching a playlist, you'll start with the video that was added first, and the last video you watch will be the final one that was added. Trees are a category of data structure that, as you might have guessed by the name, resemble trees. Trees have nodes which are connected to each other by edges. The first node in a tree is called the root node. Nodes have a parent-child direction, where one is a parent node, that leads to another node, which is a child node. Oftentimes, the parent nodes are sometimes just called nodes and the child nodes are called leaves. There are tons of tree-based data structures, but in this video, we'll be talking about binary trees, and in particular, binary search trees. A binary tree is a tree where each parent node has up to 2 children nodes. A binary search tree is a type of binary tree where all left children nodes are less than the parent node, and all right children nodes are greater than the parent node. These binary search trees make it very easy to search through large amounts graphs. Lastly, we have graphs. Graphs are basically models for a set of connections. Like trees, graphs are made up of nodes and edges. In fact, trees and even linked lists to an extent are technically types of graphs, but graphs can get a lot more complicated. In a graph, there are fewer restrictions than with trees. Nodes can be connected to any amount of neighbors. Graphs can be directed, where nodes point to other nodes, but they can also be undirected. Some graphs have cycles, where 2 nodes both point to each other. The edges between nodes can also be weighted, where the path has a value associated with it. As you can see, graphs are very complicated, which is why many people consider them to be one of the hardest data structures to learn. For now, let's see an example where graphs are useful data structures. Imagine you're running errands and you have 5 different stores to visit. We can represent this as a graph, where each store is a node and each edge has a distance. Using this data structure, we can develop an algorithm that allows us to calculate what the shortest route between all 5 places is. There are endless applications for graphs, which is why they're such an important data structure to understand. Thanks so much for watching. If you enjoyed this content on data structures and want to see more data structure videos, comment down below and leave a like on the video.